Alright, hello. So, there's a couple of questions in the homework from chapter 1 where they're talking about a proof by induction after you've done a recurrence relation. Now, recurrence relations are really useful when you've got proof by induction because they are set up to get the next term. So if you're assuming the kth term, they're all geared up for you to get the k plus 1th term. So here's a recurrence. So this would be like a typical question. So you've got a recurrence relation and it's a particular type. And this one is going to be a failure case. You know it's going to be a failure case because your complementary function is going to be in exactly the same form as your particular solution. So you could set off and not think about it as a failure, and then when you try and work out what lowercase a is, you're going to end up with a nonsense. So I'm going to start off knowing that it's a failure. So I know that my solution to the recurrence relation, so the first part of this question is solve the recurrence relation. And of course, solve the recurrence relation means take it from a recurrence relation to a position to term formula, or find the general term. So I know my general term is my complementary function plus my particular solution. Now my complementary function is 3. My complementary function is capital A times 3 to the power n. And my particular solution, because I know that this is a failure case, instead of it just being a times 3 to the n, it's going to be n times a times 3 to the power n. So the first thing I'm going to do to work out my particular solution, my value of a, is substitute this into my recurrence relation. So if I substitute this into my recurrence relation, I'm going to get, so here's my recurrence relation. And if I substitute my particular solution in, I know that the n plus 1th term, I replace the n with n plus 1. And so it's 3 times my un. So what I'm now going to do is rearrange this to get everything in terms of 3 to the n. So I'm going to rearrange this. I know that 3n to the n plus 1 is 3 times 3 to the n. So I've got n plus 1, 3 to the n equals 3an plus 1, 3 to the n. So all I've done there is I've rearranged it so I can easily see my coefficients of 3 to the power n. So if I now compare those coefficients, on the left I've got 3an plus 3a, I've expanded that bracket, and on the right I've got 3an plus 1. I can take 3an off both sides, so 3a is 1, therefore a is a third. So I know my particular solution is a third n times 3 to the n, or if you prefer, you could write that, there's my form of my particular solution, I could write that as n times 3 to the n minus 1. So now if I go back and combine that with my complementary function, so I've got a times 3 to the n plus my particular solution, so n times 3 to the n minus 1. I need my initial condition, so I go all the way back to the beginning. So I know that when n is 1, u1 is 1. So I'm going to replace n with 1 and u1 with 1. So that's going to be 1 times a times 3 to the 1 plus 1 times 3 to the 1, take away 1. Obviously that's 3 to the 0. So I'm going to end up with 1 is 3a plus 1. And I can see that a is going to be 0. So I'm going to end up with my nth term as n times 3 to the n minus 1. So that's the first part of the question. You've solved the recurrence relation. All the question's now going to ask you to do is prove that by induction. So you know that when you're asked to prove anything by induction, the first thing you do is you check for your basis case. So when n is 1, work out what u1 will be. So 1 times 3, the 1 take away 1. u1 is 1, and if you go back to the very beginning, we know that that is true. So we would say that that holds for your base case. Your next step, your inductive step, is you assume that what you're trying to prove, and this is the thing you're trying to prove by induction, you assume that that's true for n equals k. So you assume that's true. You want to show that this holds for n equals k plus 1. You want to show that for n equals k plus 1, that u k plus 1 is going to be, and what you want to show, and you can write it out so you can clearly show it, is you want to replace these k's with k plus 1s. So k plus 1 times 3, and if you replace this with k plus 1, you'll get k plus 1 minus 1, which is just that. So that's what you want to show. So all you're now going to do is use your recurrence relation. So your recurrence relation is ideal for this. Go back to the very beginning. Right, there's your recurrence relation. So your recurrence relation says that the n plus 1th term is 3 times the nth term plus 3n. So if you use that, so the n plus 1th term is 3 times your nth term plus 3 to the n. So you know that using that, your k plus 1th term will be 3 times your kth term, which is this term here, k times 3 to the k minus 1 plus 3 to the k. You know that that's 3 to the power 1, and if you multiply this bracket by 3, you'll get k times 3 to the power k plus 3 to the power k, and then all you're going to do is take out a factor of 3 to the k, which leaves you with k plus 1. So you've shown that it holds. So it holds. And then, as you've done loads of with Miss Innes and Pure Core 1, you would write your conclusion.